So we're going to finish up, or possibly finish up, our discussion of the first law. There's actually quite a bit more in these notes than I thought, so we'll look through them as best we can, and then we'll take a quiz the last 20 minutes of the class. Any questions before we start?
What are the answers to the quiz?
14, 12, and I don't know. Mostly it's a matter of just seeing that you watch the videos and work through how the process is. So, and I can see the video statistics, so I know, everyone watched at least once, so that's good. We have 30, 40 hits, and that's usually indicative of people studying. Again, that drops off the course of the semester.
I have a question. So, do we always assume that the hit capacity at the constant volume always equals like 1.5 R? Or I mean, if
Well, for an ideal gas, you can.
It's like a universal thing, just theoretical issue.
I would say that when you're making problems for students to solve, it's true. In real life, we actually make measurements of heat capacities. And in fact, all of these physical properties, the heat capacity, the expansivity, the elastic constants. The elastic constants, turns out, those are second derivatives of the free energy with respect to the strains. So the name of the game really is to determine the free energies. And once you have the free energy, that just tells you everything about the system. So how do you get these free energies? And well, the way we do it is we back out, say, okay, so if we measure these 5 things, this gives us the free energy in this amount of phase space or our design space. If you want to say, oh, I want to add magnetism, well, then you have a whole nother set of constants you have to measure, and that will give you a free energy. And the free energy is a continuous, smooth function. It doesn't have disruptions. The free energy we're looking at is only the free energy for one particular phase. So, for example, you can have 2 phases, and those 2 phases are going to be a crossing point, and when we talk about phase transformations, for example, heat capacities in a real material, they go like a little spike. And that's not about thermodynamics, that's about there being a discontinuous transition as you go from one curve of free energy from, say, phase liquid to phase gas. There's going to be a discontinuity. But just the thermodynamics of a single phase is smooth. The challenge is that the practical challenge is that we have these nice smooth curves, and you can measure them, but you can only measure them where the phases exist, right? You say, well, what's the heat capacity of ice at the boiling point? We don't know. So that's where we try to use theoretical methods to be able to extrapolate these free energies beyond just the range that we can measure them and out some. The good news is we oftentimes have functional forms that we know are right. So we'll have and we'll talk about that a little more when we get to heat capacities, that we do know, for example, our heat capacities, which is T, they tend to look like that. So this, down here you have the low temperature regime when you've got a polymer which goes as T cubed, and out here it's roughly linear. And experimentally, you'll typically have values that are out here. When you start getting this lower region, things get a little bit wonky, but we know what the functional form is, so we're both using the physical measurements of, say, heat capacity or whatever else to get these functional forms. There's a method called CalFAD. They make a software package called ThermoCalc. The generic term is CalFAD, and it's making phase diagrams from thermodynamic data. And the heat capacity will have some polynomial shape and all these other constants. You do the best to fit those from experiment, and then that will give you the free energies for each of the phases, and then you can use those to get the equilibrium phase diagrams. I'd love to teach that in this class, there's just not enough time. But I know that there's kind of general interest in the faculty, seeing people trained in this. That was a very long answer. But anyway, so where we were last time we finished up talking about this whole general form of U. I made it long because if the last student walk in, U is equal to U I. One, two, n, one plus plus b, plus u, d, j, 1 to that j minus 1, j plus 1, n, j plus that. N and zero. So these are the three general expressions. And in this set are our set of independent variables. We're talking about an ideal single component gas, so we're talking about pressure, volume, temperature, but you can go to stress, strain, magnetization, electric fields, those all fit in here. You can even do gravity, so you can talk about, in grad school, one of the problems we solved for the entropy as a function of height in the gas as you go higher, as you have a change in pressure. So gravity becomes there. And we had minus W because our system is defined as work going out and heat going in, and the system is in contact with the universe through some wall, and we can define what that wall is. Remember where we ended. So everything not heat, and this is purely heat. So anytime we talk about having a system in which that is thermally insulated from the universe, that gets rid of Q. And anytime you have something in which work is forbidden, you've got to say a rigid wall between it, and W goes to 0. And as a consequence of all this, we wound up with our expression for U equals U T V plus partial of U with respect to temperature B T. for our ideal gas. And I mentioned last time also that when we're talking about our Q, we did del Q P constant volume or pressure. So that's where we ended. And what we'd like to talk about today is enthalpy and where enthalpy comes from. So we had our expression here. We can rewrite that as Q equals U plus W is equal to delta H H2 minus H1. And we're defining this as our enthalpy. Now, in the case of our ideal gas, this W is equal to del P V is equal to P delta V plus V delta P. We say that, constant pressure and our delta P goes away, and that means that now we can write this as delta H is equal to delta U plus P delta V is equal to U2 minus U1 plus P V1, sorry, V2 minus P V1 is equal to U2 plus P V2 minus U1 plus P V1. And this then is H2 minus H1. So our expression for the enthalpy, H is equal to U plus P V. So that's great. This enthalpy is a state function. The thing that I want to point out is where this came from. This came from the assumption of, the system being an ideal non-reactive gas, single component. It came from the assumption that pressure is constant, and you kind of turn the crank, and this is what comes out. You don't need to use this as your expression for enthalpy. You use this as your expression for enthalpy. And then you have to define for yourself, or for your system, what work is. If there's a stress strain term in there, then that W goes into here, turn the crank, comes out, and you wind up with a different expression for enthalpy. And that's also something that I think the way we teach this, particularly in undergrad, is say, well, enthalpy is U plus PV. And this is, in our very limited case, which doesn't really exist in real life. Our real life problems are more complicated because there's a lot of things we're interested in, and as material scientists, we're interested in solids. Stress and strain are a big thing. And be aware that those stress and strain terms just fall through. It's also worth pointing out that this, as I said, is a state function. this is also what I call one of the games of thermodynamics. It's moving between state functions, and we'll talk about this in more detail when we get to free energies, but there are many ways that you can express a function that describes the state of the system. We had energy, and now we've got enthalpy, and then we can have a Helmholtz free energy, we can have a Gibbs free energy, we can have open systems. There's lots of different expressions for it, and what we're essentially doing is we're going through a coordinate transformation. And that's what we're doing here, and we'll see this more explicitly when we talk about Legendre transforms. So, I said this is the state function. And what that means is it means that all of the wonderful properties we talked about before, as far as being single valued, being independent of path, being able to be expressed in this type of differential form, that all holds true for all the state functions. And again, we'll come back to that a little bit later. So, enthalpy, okay? And the general idea that it's more or less a coordinate transformation. So, let's talk about measurables. And in particular, heat capacity. Heat capacity is kind of a special measurable. There are lots of others, right? We talked about 3 of them last lecture, I think on Wednesday. Heat capacity is kind of a special one because we can integrate heat capacity to get both the enthalpy and the entropy, and we'll talk about how those are related to Gibbs free energies. So we'll talk about this a little bit more, and we're going to use the C for that, which is basically Q over delta T. Sort of saying that the heat capacity is the energy, or I should say the change in energy with change in temperature, or the Q delta T. So we talk about, the capacity to store energy in the form of heat. Now there's 2 ways we can write this. We can write it as CV is equal to del Q T B, and have it a constant volume heat capacity. And if we have that, then we have U by dt B, which gives us the U equals dt, and we can integrate that with the energy. Or we can do constant pressure Cp is equal to del Q by dt. P is equal to the H dt constant P H dt. And we get the enthalpy if we have the constant pressure heat capacity. Another notation of, oh yeah.
In the problems that we went over in the videos, we multiplied by number of moles.
Yes, I'm just about to say that.
Alright.
So this is a joule per Kelvin. So we're gonna have another notation here where we're gonna have it per mole. So this is CV the Kelvin, and if we have a molar quantity, the way that I've been writing into my notes with a little CV, so I just draw a line through it. You can make a sentence or whatever. I needed something while I was writing my notes, and this is joule per Kelvin per mole. So this is molar quantities. So something to comment on is in fact going back to these, and I have my notes at this point. I have no idea why I put it here, but it's worth commenting on work briefly. Comment on work. We have the work is always two variables. And the way to think of this is if you go back to your undergrad physics class, you remember that you had some problem you worked out where you had some block, you applied a force to the block, that force moved the block by some delta x, and you said that the work is equal to force as a function of x, or if it's constant, that's just force delta x, or if force is non-constant, you got some variable friction there, then work is equal to force as a function. D work is a function of force dx. You integrate from 0 to w from x1 to x2, 1, x2, and that's how you get the work. Same is true here. When you think about work, think about pressure as a force, and it's expanding against a volume. Here, we've got a block, we've got force, we're moving the force. The same thing is true when we talk about other things. For example, electric field. Here we have an electric field, and it's working against the internal electric displacement. That's the internal polarization. Right? If you have stress strain, you have stress, and that strain is the strain that's working against. There was this guy named Lev Landau who was brilliant, and he couple textbook series he wrote in the Soviet Union when he wasn't being shoved between prison and mental institutions. He wrote his entire thermodynamics, and he used the units of force and volume for everything, including the enthalpies and entropies. Because you can think about, when we get to the free energies, that free energy is the S dt, so that's also the same functional form as this. So when you're going back and you're modifying your enthalpy terms or what have you for your real work, make sure that you understand the force and the conjugate volume it's acting on, how the units work, and follow those through your derivation, because that's a place you can get stuck. That's the end of the set. minutes here. In that time, I want to talk just briefly about heat capacity some more, and then on Wednesday we will hopefully finish up the first law and maybe start into the second. So continuing our discussion of heat capacity, one thing that is worth talking about how these two are related. And they're related. Your book has a little proof, and I'm going to skip that and just kind of jump to the conclusion here, in as much as Cp minus Cv is equal to R, your gas constant, so that's one relation that's useful. The other is this idea of the relationship between pressure and volume in adiabatic. Okay, so change colors again. So consider an adiabatic system. If you have an adiabatic system, that means that Q equals 0. Only, and that means that the Q minus delta W is equal to the U at 0. Work, we have to figure out what we want to use for that. Ideal gas work, again, is PV. Oh, sorry, constant pressure. Constant pressure. Putting in for P, P equals nRT over V, n equals 1, so I have a 1 mole system. Means that, and also substituting for U, what we just erased from over there, which was U is equal to C E T. Go to C E T equals negative RT over V. T on that side, and then integrate from T1 to T2, V1 to V2, give us CV ln T from T1 to T2 is equal to negative R natural log V from T1 to V2. Which then lets us have natural log V1 over V2 Natural log T2 over T1 CV equals natural log V2 1 over V2 R. I reverse those using the negative, getting rid of the negative from the exponential. Meaning that V1 over V2 R over CV equals T2 over T1 CP minus CB equals R CP over CV minus 1 equals R over CV. That is a term that your textbook defined as gamma, and surprisingly we will too. But ultimately this gives us P1 gamma 2 gamma constant. So why do we care about this? Well, we care about this because with ideal gases, this is useful, this is necessary. This equation is necessary. What we also care about is that it doesn't have to be an ideal gas. We just happened to use an ideal gas to be able to work with PDB at constant pressure, 1 mole of gas, and we have this analytical expression. It could be anything else. It could be stress strain, it could be something else. But the trick is, when you're working, you can't just use this equation, but you have to go back and think about, what is my system? What do I have to work with? What are the work terms? How do they fit in here? What things get canceled? Do I have some expression? This is going to be something you fit, right? You have a bunch of data points and you got an idea of how whatever stress and strain are related, or stress and temperature are related. You put into here, and then you step through this, and you'll wind up with some analytical expression like this. You have a question in the back?
The gamma, that's just CP over CV,
Yeah.
correct? It's not the -1?
Yeah.
Okay. Just want to double check.
So I guess I don't have much time here, but what I really want to emphasize here is that all of your thermodynamic education so far has come from your chemistry department, or from a chemist that's working in a materials engineering program. And they all think in terms of gas, because it's great, it's handy to use. The stuff we're interested in is not gas, and it just means that it gets a little bit more messy, but you have to start from the beginning every time that you're working, and just to make sure that you can actually trust the things you were taught. So with that, we'll take a quiz and go from there.